Okay, so now we're going to turn our attention to the titration of a weak acid or a weak base being titrated with a strong base or a strong a strong acid, right? Because of course, a weak acid would be titrated with a strong base, and a weak base would be titrated with a strong acid, right? So the way that the titration of a weak acid and base differs from that of a strong acid or base is because after the neutralization is complete, and if you're left over with some of the weak acid or base, those are going to ionize, and you're going to have to make an ice table for those weak acids and bases present. So what we're going to do is, number one, we're going to determine the concentrations of each species after the neutralization reaction with the strong titrant is done. So assume no ionization of any weak acid or base has occurred yet. So again, after the neutralization is complete, we figure out how much weak acid, weak base do we have left over. And then if any of those remain, what we're going to do is we're going to make an ice table either with the weak acid, and for that we would use a Ka, or we could make an ice table using a weak base. And for that we would use a what? A Kb, right? So you just have to kind of take these all as a two-step approach. And what you're going to see in the problem that we're going to take a look at is that once we reach the half equivalence point and equivalence point, sometimes we can simplify things a little bit. Okay, so consider a solution of zero point 0.1 molar acetic acid. 40 mils of this solution is titrated with zero point 0.2 molar sodium hydroxide. Calculate the pH after the following volumes of sodium hydroxide have been added to the solution. They give us the Ka for acetic acid is shown here. And so identify the following points. So we're going to look for the half equivalence point, the buffering region, and the equivalence point. So let's start out with the first one, which is going to be when we have added no sodium hydroxide. So at this point, all we have is our 40 mils of our excuse me, zero point 0.1 molar acetic acid. So for acetic acid, I'm going to write HO HOAC. And for the conjugate base, so for the acetate ion, I'm just going to put OAC minus like this. So when you see the acetate ion, it'll be OAC minus. All right, so let's start it with our acetic acid, which is a weak acid. When you put a weak acid in water, it's going to donate a proton to water to give you hydronium, and of course the acetate ion like this. So we're starting out with a concentration of 0.10 molar of our acetic acid. We're going to assume we have none of these. We are going to lose something here. We're going to gain a certain amount here. And at equilibrium, we're going to have 0.10 minus x. Here we'll have x, and here we will have x. So what we're going to do is we're going to assume that we can ignore this x here. And of course, we'll check our assumption. And so we know our Ka, since we're starting out with our acetic acid, we're going to use Ka. Our Ka is going to be equal to the concentration of hydronium times the concentration of our acetate divided by the concentration of our acetic acid, like this. And so our Ka is 1.8 times 10 to the negative 5, and that's going to be equal to x squared over 0.1. So we solve for x, which is going to be equal to the concentration of hydronium, and I've gone ahead and done this already, and you end up with 1.3 times 10 to the negative 3. Now, if we want to do the check here to make sure our assumption was okay, we would say 1.3 times 10 to the negative 3 divided by our initial concentration, which is 0.1, and we'd multiply that by 100%. So let me just grab my calculator here. 1.3 times 10 to the negative 3 divided by zero point 0.1, and we multiply that by 100, and we end up with 1.3%. And so our assumption is okay because 1.3% is less than 5%. So we're good to go. And so now we can evaluate our pH, and pH is going to be equal to the negative log of the concentration of hydronium, and we end up with our pH as being equal to the negative log of 1.3 times 10 to the negative 3, and we end up with our pH as being equal to 2.8 7. Okay, so that is our pH after we have added 0 mils of our sodium hydroxide. So now what we're going to do is we're going to go to a clean page and we're going to figure out what's the pH after we've added 5 mils of sodium hydroxide. All right, so now we're going to react our acetic acid with 5 mils of sodium hydroxide. So our sodium hydroxide is going to react with our acetic acid. And when they react, we're going to end up with a sodium ion and an acetate ion. The acetate ion is really the only one we need to be concerned with because sodium is not going to affect the pH. And of course, here you're also going to end up with water. I'm kind of running out of space here, but you're also going to end up with water. And that's not going to be pertinent for our equilibrium. So we're going to start out by figuring out the number of moles of our sodium hydroxide. So we're adding 5 mils, which is 0.00500 liters multiplied by 0.20 moles per liter. That gives us 0.0010 moles. We can do the same thing for our acetic acid. Maybe I'll color code that. So there we go. We'll turn it blue so we don't get mixed up. All right, so for our acetic acid, we have 40 mils of 0.1 molar, and you might know this calculation from previous problem, but we have come on, we have 0.04000 liters times 0.10 moles per liter. That gives us 0.0040 moles. And so that is our initial number of moles of each, the acetic acid and the sodium hydroxide. So we see the sodium hydroxide is the limiting reactant. We have 0.001 moles of it, and we have 0.004 moles of the acetic acid. So we have 4 times as many moles of acetic acid as we do sodium hydroxide. So we're going to do our change. So we're going to lose all of the sodium hydroxide. We're going to lose 0.0010 moles of this. And of course, we're going to gain 0.0010 moles of the acetate ion. I'm going to leave the sodium out, and if I'm going to leave the water out too, because they're not pertinent to pH, and I don't want to squeeze things too much. So we have 0 here, 0.0030 moles here, and we have 0.0010 moles here. All right, so now what we're going to do is we can see that all we have left over is we have our weak acid and we have its conjugate base. We have a certain number of moles of each one of those. So what I want to do is figure out the concentration of each one of these. And so we're going to divide by the total volume. And our total volume in this case is going to be 40 plus 5. So that gives us 45 milliliters. So what I'm going to do here is I'm going to divide by 0.004500 liters divided by 0.00, oops, 0.0, excuse me, 4500 liters. So now we're going to figure out the concentration of each one of these. And you're going to have to bear with me because I didn't do this, 0.045. So we end up with 0.067 molar of our acetic acid. And for our acetate ion, we have 0.022 molar. So that's our equilibrium concentration. And so now what we have to do is we have to make an ice table where we put in the concentration of our weak acid and its conjugate base. So since they've given us the Ka, I'm going to put in the concentration of the acetic acid, or I'll put in the acetic acid first rather. So I have my acetic acid plus water is in equilibrium with hydronium plus my acetate ion. So I know initially I have 0.067 molar here. I have 0.022 molar here. Now, if we're trying to find the pH, we are trying to find the concentration of hydronium. And we're going to assume that initially we have none of these. So the equilibrium is going to have to go to the right in order to make some hydronium, some X. So we'll put these here. And we're going to assume that X can be negated, and we'll check that after. So 0.022 molar, like that. So now, in order to calculate the X value to get my concentration of hydronium, I'm going to use my Ka value, and I'm really running out of space here. My Ka value, which is 1.8 times 10 to the negative 5, is going to be equal to x multiplied by 0.022 divided by 0.067, like this. And so when we solve for our x, we end up with, we get 5.5 times 10 to the negative 5 molar. And so that's the concentration of our hydronium. So just in the interest of space, I'm going to put in the negative log of 5.5 times 10 to the negative 5. And we get a pH that is going to be equal to, we end up with 4.26. So the pH is going to be equal to 4.26 is going to be our answer here. Now, it says here, identify the following regions: the half equivalence point, the buffering region, and the equivalence point. Well, the equivalence point is when the number of moles of acid and base are equal to each other. The half equivalence point is when we had half the number of moles of base as we do of the acid. So we haven't reached that yet. But right now we are in the buffering region, right? We are in the buffering region. Right now, how do we know that? Because we have a solution at the end that contains a weak acid and its conjugate base. So of course we're in the buffer region. And so you can check me on this if you want to, but you could solve for this pH here using the Henderson-Hasselbalch equation. Okay, so again, you could try this using the Henderson-Hasselbalch equation, and you're going to get the exact same answer. Why? Because we are in the buffering region. All right, so what's going to happen if we add 10 milliliters of sodium hydroxide? All right, so now we're going to add 10 milliliters of sodium hydroxide, and we're adding 10 milliliters of zero point 0.2 molar sodium hydroxide to 40 mils of our 0.1 moles of acetic acid. So let's write out the neutralization, which is our sodium hydroxide plus our acetic acid is going to give you the acetate ion plus sodium plus water. Of course, we don't have to worry about the sodium concentration or water because those don't affect pH. So for our sodium hydroxide, we want to figure out the number of moles. We have 0.0100 liters. No, I'm missing a zero there, aren't I? 0.00. There we go. Liters multiplied by 0.20 moles per liter. So that means the initial number of moles of my sodium hydroxide is going to be 0.0020 moles. For my acetic acid, and again, what I'll do is I'll color code this blue because I don't have a lot of space here. So for my acetic acid, I did this one before. I have my 40 mils of 0.1 molar, so I'll just write it down here. We have 0.0040 moles. We're going to assume 0.000 here. All right, so change is, you can see that the sodium hydroxide is still the limiting reactant, and so we're going to lose all of it. So we're going to lose 0.0020 moles here. We're going to lose 0.0020 moles here. We're going to gain 0.0020 moles here. And then the other ones, I'm not going to worry about them because they don't affect pH. And so equilibrium, I have none of this. I have 0.0020 moles here and 0.0020 moles here. So now we are at the half equivalence point. So this is the half equivalence point because half of the analyte has been neutralized. So you can see that we have an equal number of moles of our acetate and our acetic acid. And so if we calculate the concentration of each of these, so we're going to divide by our 50 mils because we're combining 10 mils and 40 mils. So that makes 50 mils. So 0.5000 liters. 0.0050 liters. And so we end up with a concentration, equilibrium concentration for both of these, which is 0.040 molar, 0.040 molar. So now what we're going to do is we're going to make a new ice table with the concentration of our weak acid and the concentration of our weak base, which are equal to each other. Now, if you're astute, which I know you all are, you probably realize that you don't really have to do that to evaluate the pH. But since I'm your instructor, I'm going to show you how to do that very quickly. So what I'll do is I'll put a line here, and we're just going to do this very quickly. And we're going to say, okay, well, I have my weak acid and its conjugate base. They gave me a Ka, so I'll just write out the same equilibrium expression that I did in the previous section. And we know initially we have 0.040 molar of this, 0.040 molar of the acetate. So I put that in the wrong spot. Move that over here. And we're going to assume we have nothing here. So change, we're going to have to lose x. Here we'll gain x. Here we'll lose, or sorry, here we'll gain x as well. So at equilibrium, we're going to assume that x is so small it can be ignored. And we can check that too. We have 0.040 molar. Here we have x. Here we have 0.040 molar. Well, you can see that when we do our expression for our Ka, we're going to end up with 1.8 times 10 to the negative 5 is equal to x multiplied by 0.040 divided by 0.040. So you see that these two cancel out, and our x, which is equal to our concentration of hydronium, is going to be equal to 1.8 times 10 to the negative 5, like this. So we can say that when we're at the half equivalence point, our Ka is going to be equal to the concentration of our hydronium. And we can also say that pKa is going to be equal to pH. So we're going to calculate our pH, which is going to be the same thing as our pKa, the negative log of 1.8 times 10 to the negative 5. And we end up with a pH that is equal to 4.74. So again, what you need to remember is when you're at the half equivalence point, when the number of moles of weak acid and weak base are equal to each other, the pKa is going to be equal to the pH, okay? Or the Ka is going to be equal to the concentration of hydronium. Furthermore, you could say the pKb would be equal to the pOH, but we'll just stick with acids for this one. So now we're going to move on to once we've gone past the half equivalence point, we're going to look at section or part 4, where we had 20 mils of our sodium hydroxide. And so now we're at 20 mils of our sodium hydroxide. And I'm going to go a little bit faster on this one. I'm going to assume that you know how to multiply volume by concentration to get number of moles now. So we're going to say our sodium hydroxide. So we're going to say that our sodium hydroxide plus our acetic acid is going to give us an acetate ion plus sodium ion plus water. Again, sodium and water don't affect the pH. So to figure out the number of moles of our sodium hydroxide, we're going to take our 20 milliliters and multiply it by the concentration. And when we do that, we end up with 0.0040 moles. Well, you know by now that when we have 40 mils of the 0.1 molar solution of our acetic acid, we have 0.00040 moles. So we have the same number of moles of acid and base. And so this is the equivalence point. Again, it's the point where the number of moles of acid are equal to the number of moles of base. All right, so this is initial. We're going to assume nothing here, so we'll do our change. So we're going to lose everything from both of these, 0.0040 moles. We're going to gain 0.0040 moles of our acetate ion. So at equilibrium, we're going to have none of this. We're going to have none of this, but we'll have 0.0040 moles of our acetate ion. So now we need to figure out the concentration of our acetate ion. And so we're going to divide that by the total volume. which is 20 mils plus 40 mils, so that's 60 milliliters. So we're going to divide by 0.06000 liters, and we end up with an equilibrium concentration, which is going to be equal to 0.067 molar. So that is our equilibrium concentration of our acetate ion. So now we need to set up an ice table with the conjugate base, our acetate ion, and we need to figure out the concentration of our hydroxide so we can evaluate a pOH. So now we need to write out the equilibrium expression for the acetate ion in water. And acetate is a base, so it's going to pull a proton off of water to give you acetic acid plus hydroxide ions. We know our initial concentration is 0.067 molar here. We have 0 and 0. We're going to lose X, we're going to gain X, we're going to gain X here. And at equilibrium, we have 0.067 minus X. Here we have X and X. We're going to assume that we could ignore the X. And of course, you can check that, but we're just going to make that assumption for now. And I can tell you I've already done the problem, so it's going to work out. So we're going to need our KB this time, and they didn't give us the KB, but we can figure out the KB. So our KB is going to be equal to KW divided by KA, which is 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. All right, so when we solve for our KB, we get 5.6 times 10 to the negative 10. So I'm just going to scooch down here. So we're going to say our 5.6, our 5.6 times 10 to the negative 10 is going to be equal to x squared over 0.067. When we solve for x, which is going to be equal to the concentration of our hydroxide, we end up with 6.1 times 10 to the negative 6 molar. And if you want to check, okay, I know I don't always do that, but you could put in your calculator 6.1 times 10 to the negative 6 divided by 0.067, multiply that by 100, and you get nowhere near 5%. And so the assumption is valid. So we're going to calculate our pOH, which is the negative log of 6.1 times 10 to the negative 6. And our pOH ends up equaling 5.21. And so our pH is going to be equal to 8.78. There you go. So that's the answer to part 4. So again, we're at the equivalence point here, where the number of moles of acid is equal to the number of moles of base. And so you can see here that if we've neutralized all of the weak acid, all that's left over is weak base. And so it makes sense that the pH at the equivalence point would be greater than 7, right? It's because it's going to be a basic solution at this point. All right, so let's move on to the last part. All right, and in our last part, we're adding 25 mils of sodium hydroxide. So we're past the equivalence point at this point. So I'm going to write out my sodium hydroxide plus my acetic acid is going to give me my acetate ion plus sodium plus water. Again, as always, I'm not interested in the sodium or the water. This time, I'm not going to go over every little dirty calculation here. So I have my 25 mils, so I divide that by 1,000, 0.025 liters multiplied by my concentration, and I end up with 0.0050 moles of my sodium hydroxide. As always, I'm starting it with my 0.0040 moles of my acetic acid. So I'll put zeros here. So you can see now that the weak acid, my acetic acid, is the limiting reactant. So we're going to lose, oops, we're going to lose 0.0040, lose 0.0040. We're going to gain 0.0040 moles here. And so at equilibrium, I'm going to be left over with 0.10 moles of my sodium hydroxide, none of this, and 0.0040 moles of my acetate ion. Well, my sodium hydroxide is a strong base, right? Sodium hydroxide is a strong base. My acetate ion is a weak base. And of course, my acetic acid is a weak acids. So the only one here, the only species that's going to be pertinent for my pH is going to be the concentration of the hydroxide that comes from the sodium hydroxide. Because the concentration of hydroxide ions that I get from the sodium hydroxide is going to be much, much larger than any concentration of hydroxide ions that I would get from the equilibrium of the acetate ion in water. And so we have the concentration of our hydroxide ion, we're going to divide by the total volume, which is going to be 65 milliliters, so 0.0650 liters. And we get our equilibrium concentration is going to be 0.015 molar. So remember, when sodium hydroxide dissociates, right, NaOH, it dissociates 100% to give you sodium ions plus hydroxide ions. And so without building an entire ice table, if you're starting it with 0.015 molar here, after everything has reached equilibrium, or not equilibrium, but once the whole dissociation is complete, you're going to end up with a concentration of hydroxide that is 0.015 molar. So we can evaluate our pOH. And our pOH is going to be equal to the negative log of 0.015 molar, like that. So our pOH is going to be equal to 1.81. And so our pH is going to be 14 minus 1.81. And so the pH of our solution is going to be 12.19. And that makes sense that it would be extremely basic because the major player in my solution is going to be the sodium hydroxide that's left over. And so what does our titration curve look like for the titration of a weak acid with a strong base? Well, you can see that we start out with a low pH and the pH increases slowly because we haven't neutralized all of the weak acid yet. And so until we neutralize all of the weak acid, we are in the buffer range at the very beginning. And since we're titrating with a strong base, once all of the acid has been neutralized, then we're going to be left over with our weak base. And so you can see that our equivalence point is going to be greater than a pH of 7. And then after equivalence point, well, then the pH is going to be super high. So what did we learn? We learned that the pH at the equivalence point, when you're titrating a weak acid with a strong base, is going to be greater than 7. Before you reach the equivalence point, you're going to be in what's called the buffer region, and you can use the Henderson-Hasselbalch equation to solve for pH at that point. The curve isn't symmetrical. And then we also saw that at the half equivalence point, that's when you've added enough of the base in order to neutralize half of the acid. So you have an equal concentration of your weak acid and its conjugate base. And so those cancel out when you solve the equilibrium. And so at that point, at the half equivalence point, the pH is going to be equal to the pKa. So just a little, fast way to solve problems there.